Hello everyone, welcome to another one of our research videos where we give a brief summary of scientific research we've undertaken. My name is Raphael Spiekermann, I'm co-founder of Vedantia Research, and today I'm going to talk about quantifying the effect of trees in terms of stabilizing slopes to reduce landslide erosion. This work is based on my PhD thesis, which is also freely available online if you want to read up on that. My research during the PhD was aimed at quantifying the effectiveness of trees in reducing erosion and sediment delivery to streams from landsliding. And in this talk I'm focusing on how we can determine where trees are needed most from a soil erosion point of view in New Zealand's hill country, and what effect we expect those trees to have depending on their location in the landscape. So first, just a little context to this work. We see a bunch of maps, and what they show is basically the evolution of deforestation in New Zealand following first the arrival of settlers from Polynesia around 800 years ago, and then Europeans in the 1800s. It resulted in extensive deforestation and a landscape response of high rates of erosion and sedimentation. And this is what that would look like, the high rates of erosion. So this is also where my research was undertaken in a large study area in the Wairarapa, and this picture illustrates the problem that I'm addressing in the video. We see a devastated landscape following the rainfall event in 1977, and it was mainly in response to that event that lots of trees were planted. And today, the picture is quite different. We see a large amount of widely spaced trees that were planted of various species, and yet we still have these periodic heavy rainfall events that trigger many more landslides. I mapped 43,000 of them in an area of around 84,000 hectares, and these were triggered mainly in 2005, 2006 and 2009 storm events. And so the obvious question to me was, at the beginning of my PhD, how effective are these silvopastoral systems with the many widely spaced trees that have been planted? How effective are they at reducing landslide erosion? Now, there are obviously many different erosion processes, so why the narrow focus on shallow landslides? In a book chapter that was published by a former colleague of mine, Les Basher, also a great read and freely available, I can post the link below the video. He provides a really good overview of erosion processes in New Zealand based on the New Zealand Land Resource Inventory, and there he finds that mass movements, which are movements of soil and rock debris down slopes in response to the pull of gravity, are the most widespread type of erosion in New Zealand. And the most common type of mass movement are shallow, rapid slides involving soil and regolith that are triggered by rainstorms. Okay, here's another more recent photo showing these many shallow landslides that can be triggered during rainfall events. This was in March of 2022 in the East Cape. And obviously a year later we had Cyclone Gabriel that caused even more devastation. And this photo shows a couple of these slips. I took this in the Hawke's Bay, and shows nicely that the landslides can have these very long debris tails that can deliver large amounts of sediment to adjacent stream channels. Okay, so now when it comes to trees, how can we determine whether they are effective or not, and what does it mean to plant the right tree in the right place? So first off, it can be said that trees generally have a very positive impact on slope stability. Because of the roots, they increase the soil cohesion and the hydrological processes that regulate soil moisture through interception of rainfall and evapotranspiration. Now this figure you're seeing on your right is quite thought-provoking, because what we're seeing are these landslides that I mapped here, about 43,000 of them. See a zoom in, these two yellow squares zoomed in here to show you what the landscape looks like. On average, those scars are less than 100 square meters large. But in this plot, I've plotted the distribution of landslides with respect to slope gradient. We see a very narrow distribution. Most of them are occurring between 25 degrees and 40 degrees slope angle. And in contrast, we see the poplars and willows in the same area, and the vast majority are located on slopes less than 25 degrees. Now, many of these trees will be planted for other purposes like stabilizing stream banks, but we also know that a lot of poplars and willows are planted to stabilize slopes. And ideally, we would see the distribution more closely resembling the distribution in terms of where landslides are occurring with respect to slope gradient. Otherwise, it can be said that they are not doing much to prevent landslide erosion. Now, it's obvious from this graph that I showed and that there's a relationship between landslides and slope gradient, and I could show you similar graphs with respect to rock type, for example, and other factors too. Shallow landslides in this map is shown the lithology in the study area. They occur in greater numbers on soft rocks like mudstones and sandstones compared to, for example, limestone. And so it's a problem, landsliding, that involves multiple variables because slope stability is just relatively complicated. Ultimately, it's about soil properties, hydrology, and gravitation acting on soil masses. So when trees are an additional component to the equation, it becomes no less simple. And that's why statistical models can be helpful in disentangling these various effects. So when it comes to statistical models, it's useful, or actually we need to know under which conditions landslides have occurred in the past. And with the help of semi-automated remote sensing techniques, I built this very large landslide inventory by mapping off very high resolution imagery in the Wairarapa. And these landslides become empirical observations that can be used to build statistical models called landslide susceptibility models. And the idea is relatively straightforward: to classify the land into stable and unstable areas using these variables such as lithology, slope gradient that I spoke about earlier. And the higher the probability of an area being classified as unstable, the more likely it is that this will be a site of future landsliding, because it more closely resembles areas that have been sites of landsliding previously. So that's the assumption with landslide susceptibility modelling. So how do we include the tree effect in these models? As shown in this example farm, the challenge in these silvopastures is accounting for the many widely spaced trees. And we ultimately want to know how effective those trees are at preventing future landsliding. And now with new technologies, namely LiDAR and high-resolution imagery, we can detect the individual trees and classify them broadly based on the tree canopy characteristics in the imagery. And what we see here are conifers that have been classified in the dark blue. Those are woodlots. The yellow are poplars and willows. The green are eucalypt, and a lot of the purple are carnica. And it was in the first phase of my PhD research that I then developed tree influence models, shown on the left here. And they represent the effect of individual trees as a function of distance from tree. So the tree effect reduces with increasing distance from the tree until a point is reached where there's no longer a measurable effect. And this method and the curves were published in this study, and I'll post the link below the video. Now, I then included these representations of individual trees in a landslide susceptibility model, alongside other important factors such as slope gradient and rock type, to quantify the effect of the individual trees in determining shallow landslide occurrence for a study area in the lower North Island, the Wairarapa here. So these landslides, the 43,000, were from the basis for training the model, and once trained, predictions can be made of landslide susceptibility, and this is what a prediction looks like for the example farm I'm using. We see different shades going from green to red. green represents stable areas, and the closer you get to red, the more unstable. And yeah, it's the red areas where we would expect most landslides to occur during future rainfall events. Now, the maps can also be used to illustrate the effectiveness of the right tree in the right place, but also the right tree in the wrong place, at least from a slope stability point of view. These predictions are now shown in this animation, beginning with a prediction where the existing vegetation has been removed, so it represents a treeless, like a pasture baseline. And then the next prediction is with the existing trees present, so accounting for those existing trees. And it provides quite a nice contrast between the eucalyptus grove we see on the right here, which begins with, it's a very red area, meaning it's highly susceptible to landsliding. Without trees present, this is where we would expect a lot of landslides to occur. But because the eucalypta are now present, it's turned to green, most of the area, which means the slopes have been stabilized. If you go across the ridge, you see a big basin, many poplars and willows located there, but the pattern in terms of landslide susceptibility, it doesn't change much, and that's because a lot of those trees are located in valley bottoms or on lower slopes where we wouldn't expect landslides to occur with or without trees. So they're not doing much from a landslide erosion point of view. Here the same view without the animation, just with the three classes, low, medium and high. And these three classes I'll come back to in a second. Just the photo there showing the steep slope that the eucalypt were planted on, doing a good job there of stabilizing the slope. Now, the spatial predictions of landslide probability were classified into these three classes of low, medium and high, and based on the characteristics of locations of previous landslides, we would expect 80% of future landslides to occur in the red zones and 15% in the yellow, and the remaining 5% in the green. So the red zones are much more problematic from a landslide erosion point of view. Now, this effect of the individual trees can be aggregated to farm scale to quantify the overall performance of trees in reducing landslide erosion. And to illustrate this, just for two farms, we see the distribution of landslide susceptibility classes at site 1. First, with the treeless pasture-only baseline, we see 15% of that farm highly susceptible with no trees present. That's been reduced to around 12%, that area, because of trees present. And on site 2, just to contrast that, we see similar proportion of the farm highly susceptible, 15%, but because of the trees present, it's been halved to around 7%. Now, accounting for the rate of landslide erosion across these three different susceptibility classes, and assuming that the triggering mechanism that was observed for the landslides that were triggered in the past will be similar in future, we can estimate that landslide erosion has been reduced by 17% at site 1 and 43% at site 2 due to all existing vegetation. And the photos of the two sites are quite telling. So site 2 is almost a best case scenario in terms of erosion mitigation. Site 1 just has far fewer trees, and that's why the estimated reduction is also there. So it's about number of trees, but also specifically their location in the landscape. This study was also published, and we'll be sure to include the link below. Okay, so to summarize, I think I've shown that the influence of individual trees can be controlled for with these landslide susceptibility models, and that enables us to quantify the effectiveness of the existing tree cover in reducing landslide erosion, and slopes that are most likely to be sites of landslide erosion in the future can then be identified and targeted with tree planting in future. Targeted tree planting can have a massive impact on cost effectiveness of erosion and sediment control, something I haven't talked about in this video, but it will be the feature of the next video in this series, so be sure to follow up on that. Should be a link below. And that's all for now. Hey, thanks for watching. If you enjoyed this video, make sure you subscribe. And yeah, please, if you've got thoughts, questions, comments, really interested to hear from you. You can reach out using the contact form on our website, vedantiaresearch.co.nz, or just comment below this video. Cheers.